project is on multi-core schedulers.
I'm Joseph Erickson.
And I'm Oswaldo Ramos. Our abstract for this is that multi-core systems are large systems that allow cores to run in parallel in order to handle processes more effectively. The type of scheduling that is able to lower the time for the processes to run, the power consumption, and hardware costs. Operating systems are able to use multi-core scheduling to optimize running processes and improve their usability. We wrote a paper about the findings regarding the characteristics, techniques, and functionality of core scheduling in operating systems. And we will, in these slides, present to you what we were able to find on this topic.
Here's a diagram of the multi-core systems. As you can see, there's multiple cores that each have their own cache and is connected to the operating system.
There are different types of multi-core scheduling algorithms, and a few of them are listed below. Load balancing, asymmetric and symmetric, processor affinity, and multi-core processing. Load balancing is done by limiting the loads of each element. If one processor has more work to do than others, then a portion of that load is distributed in order to keep them fairly equal.
Asymmetric scheduling is done using a master server. The master server is the one that handles all scheduling of the processes. It has a queue assigned to it, which that queue has scheduling algorithms used to help the master server decide which processes to assign to each processor. Symmetric
Processor
Symmetric scheduling is when the processors in the system assign themselves to each process. This also involves a queue, but it's just one queue and they all pull from it using a scheduling algorithm.
Processor affinity is the assignment of processes to cores based on which core is available and freed. And that means that a thread or process can be assigned differently every time and thus can be described as having affinity since it can seem to have a spontaneous assignment. Multi-core processors have several processor cores that are on the same chip, and so the multiple cores in the system allow it to divide the processes up on these cores and allows for faster turnaround and consumption of less power.
Also, I forgot to mention, sorry, in asymmetric scheduling, the processors only execute the user code. This is single queue versus multi-queue scheduling. A single queue is the simplest approach. It involves one queue that each CPU uses to decide the next process it should take on. The queue is handled with some type of scheduling algorithm, usually round robin, first come, first serve, a highest priority. This requires an affinity mechanism to limit process jumping between the CPUs. As the number of CPUs grows, the performance drops because most of the time the processes is spent in the locks. Multi-queue scheduling was created to deal with all the problems that single queue had. Each CPU has its own queue assigned to it to give confidence that each process will only run on one CPU. These queues are handled with the scheduling algorithm as well. It's usually round robin. All synchronization issues are solved by multi-queue. And here's the examples of single queue. You can see there's one queue that each CPU takes on, and it results in E going through all four. Here's multi-queue with two CPUs, which each have a queue. As you can see, B and D only go to CPU1, and CPU 0 only takes on A and C.
So there are limitations to multi-core scheduling, and some of those are the relaying of information, load estimation, allocation of resources, problems with cache affinity, and migration limits. So the relaying of information issues arise when there's not enough information being relayed about the state of the cores. So uh, it might be sent to the wrong core when it should be sent to the different one. Load estimations, that's when an estimate on how much work a core has to do is not accurate, and therefore it gets sent to the wrong core, and it could make the timing longer. The allocation of resources, that happens when things like memory is allocated incorrectly, and things like this happen, and it can exceed cache capacity of cores and then cause the system to run slower than a better allocated one would. Cache affinity, that happens when a process is ran on one CPU and goes to another CPU, and then there's a loss in performance. It's faster for it to run on the same CPU. Migration limits, sometimes limits are set into how much you could move a process. So if you move it too much, then you can no longer move it, and that would cause there to be an increase of time.
There are a lot of benefits that come from multi-core scheduling, including performance, because it's able to run multiple processes in parallel, which decreases the throughput. The more cores, the higher the performance. They are very energy efficient. There's less power consumption and longer battery life. They provide isolation because the processes are likely to the processes are less likely to interfere with one another because they are running separately on separate CPUs. This also provides no delay between the processes. This lowers the hardware costs, but there's better technology made with less computers and processors. And as the advancements are made, the hardware becomes more accessible to the consumers. Multi-core scheduling provides a reduction in scheduling time because more processes can be done in the same amount of time.
So in the past decade, there's been great improvements to multi-core scheduling, but there could be more improvements that would make it even better, such as the specialization of scheduling, which would be having more scheduling algorithms loaded into a system in order for it to best choose what to do correctly every time. It could improve the handling of large processes, and that can drastically improve the speed at which a system can operate, because large processes are difficult to execute since, of course, they're large. They must be split up and ran concurrently across several cores, and it takes time for these threads to migrate, and it becomes substantial, and it causes the system to take longer. Give more information about the processes and threads in order to better allocate where these threads and processes go. Giving the cores more information about them would alleviate some of the issues. Control where processes are cached. If a process is sent to to somewhere where it has already executed before, then it'll be cached and it'll take less time. And then the cache capabilities, increase the size of the cache so there's more processes that are stored in there for longer. Going forward, the changes we're going to be able to see is development of better multi-core scheduling algorithms, leading to faster scheduling. Hardware will become cheaper and faster, which will in turn lead to faster scheduling. There's going to be an increase of cores and chips, so more cores will be able to do the processes in about the same amount of time, so more things get done in the same amount of time. And more advanced scheduling algorithms will lead to faster scheduling.
And here are references. Thank you.
Thank you.